Hello, today I'm going to talk to you about gas properties, and we're going to use the principles of kinetic molecular theory that we just learned to make predictions and then do calculations. All right, first let's just talk a little bit about what pressure is. So I have an animation or a picture here that shows you two different people walking, all right? And you can see that the larger person, the man here, is not causing divots in the ground, but the woman who is in heels is. And that's because pressure is a relationship between force and area. So however much force you're exerting over a given area is how much pressure you have. So if you have more force, then the pressure would be higher. So if we were just looking at just the force alone, the man is going to be exerting more force on the ground because he has a bigger mass than the woman is. However, area is also a factor. So if you have more area to spread your force out in, then you're going to have lower pressure. She is putting all of her force in this one little spot here, so that's a very small area. So that's going to be a high pressure, which is why her shoes sink into the ground. All right, so in terms of gases, what this means is that if the molecules are hitting the walls of the container a lot, that's more force, all right? And so that would be higher pressure. And if we spread out the area in which they're colliding, then we would have a lower pressure because we'd have more area. All right, so we have a bunch of different laws that I'm going to talk about. I do not care if you remember the names of the laws. I want you to be able to reason your way through them. So Boyle's law gives us the relationship between volume and pressure. All right, so volume and pressure, if we think about this, if we have a balloon that has a particular pressure, or a container, and we increase the volume, now these particles have more space to move around, and so they're going to collide with the container less often, because it's a larger area, and so the pressure should go down. So this is an inverse relationship, right? And so for inverse relationships, the equation that you use is x1 times y1 equals x2 times y2. So we multiply the two variables if we have an inverse relationship. So for Boyle's law, that's going to be P1 V1 equals P2 V2. Right? I am not advocating memorizing these equations, just remembering that if it's inverse, Boyle's law, pressure and volume is the only relationship that we talk about with gases that's inverse, that you multiply, and for the other ones you'll end up dividing. So we'll do those in a second. So here we have a sample of hydrogen gas. It has a volume of 5 liters and a pressure of 1 atmosphere, right? So if we decrease the volume to 2 liters and don't change anything else, how would we expect the pressure to change? So if we had a 5-liter container and we squished everything down into 2 liters, I would expect the pressure would go up because we don't have as much space for the particles to move around, so that area has decreased. All right, but let's do the calculation and make sure that we get an answer that makes sense. So we'll plug in our initial pressure and our initial volume. We're trying to find the final pressure, and we know our final volume is 2. Right? So if we do our algebra and solve here, it's 1 times 5 divided by 2 would give us 2.5 atmospheres, which is bigger than 1, which is what we predicted. All right, the second law we're going to talk about is Charles' law. This is the relationship between temperature and volume. So if we have a balloon and we increase the temperature, the particles are going to move faster, and they're going to push more on the sides of the container and cause the volume to increase because it's pushing out more, right? So that is a direct relationship. And when we have direct relationships, we take one variable divided by the other, okay? This, it just has to be divided. It does not matter which is on the top or which is on the bottom. For ease of algebra, I usually put whatever we're trying to find on the top because it just makes it easier to solve the equation. So here we have a sample of argon gas, has a volume of 5.4 liters and a temperature of 15 degrees Celsius, all right? If we increase the temperature to 42 degrees, we would expect that the volume should increase, right? But what we're trying to find is the final volume. So I'm going to put volume on the top in our equation. Okay. One other note, all of these calculations, your temperature needs to be in Kelvin. I will give you the conversion on tests and quizzes, but you need to know that you need to use it, all right? So 15 was our initial temperature, but we have to add 273 to get it into Kelvin, right? Our final temperature was 42. Again, we add 273 to get it to Kelvin, right? And now we just do our math and solve for V2. So that'll be the 5.4 divided by 288, which is what you get when you add these two together, and then multiply both sides by 315 to get rid of the number over here. And then our final volume should be 5.9 liters. So that's a little bit bigger than the volume that we started with. All right, Gay-Lussac's law. This one relates pressure and temperature. So just like before, if we increase the temperature, the molecules are going to move faster. If the volume can't change, if we have a rigid container, then what's going to happen is, because they're moving faster, the molecules are going to collide with the sides of the container more often, and so our pressure should go up. So that's a direct relationship again. So we'll be dividing. So in the problem that we have here, we have a can of hairspray that has a pressure of 4 atmospheres at 25 degrees Celsius, and we throw it into a fire. The temperature goes up to 402 degrees Celsius. That's very, very hot. So what will the pressure be? So now let's plug our numbers in. So what we're trying to find is the final pressure. We would expect that it should be bigger than 4 because we increase the temperature a lot. And if we go ahead and solve the equation, we get a pressure of 9.1 atmospheres, right, which is a pretty big increase in pressure. All right, now for Avogadro's law, we're looking at volume and the number of moles. All right, so intuitively, you probably know that if you put more moles of gas into a balloon, the volume goes up, right? Like if you blow up the balloon, the volume's going to increase. All right, and that's a linear relationship. So if you add twice as many moles of gas, you're going to get twice the volume. It doesn't matter what the identity of the gas is. It's the number of particles that's going to be the factor. All right, so again, I just said if we increase moles, we're going to increase volume, so that's another direct relationship. All right, and in this problem, we are adding helium, so what we're trying to find is the final volume, so I put volume on the top, right? So if we have a weather balloon with a volume of 44 liters, and it has 2 moles of helium in it, right? We want to find the final volume if we add 3 more moles to give a total of 5. So you have to read these problems carefully because it's the total moles at the end that we want to use as our N2, right? Not the 3. That would be if we just added 1 mole. 5 would be what we'd get if we'd add all 3. All right, so we plug in our 44, our 2, the volume at the end is what we're trying to find, and 5 moles is how much gas is in there at the end. So go ahead and rearrange our equation and solve, and we get a volume of 110 liters at the end. All right. The last law that we're going to talk about is Dalton's law. Dalton's law deals with partial pressure, all right? And the partial pressure is the pressure that comes just from the collisions of that specific gas. So if we have 2 containers here, this one has gray particles, this one has red particles. Each of those has a pressure associated with it. And if we put them both in the same container with the same volume, so here our volume did not change, okay, then the total volume is the sum of those 2 individual pressures. That's what Dalton's law tells us. All right, but the partial pressure for each of them is how much pressure that specific gas is exerting on our container. Okay, so let's do an example. The Heliox breathing mixture of oxygen and helium is prepared for a scuba diver who's going to descend 200 feet below the ocean surface at a depth that the diver breathes a gas mixture that has a total pressure of 7 atmospheres. Okay, so that's our total pressure. For Dalton's law, we're always going to be looking either for the total pressure or using the total pressure to find individual pressures of the other gases. So if we know the partial pressure of oxygen is 1.5, then what is the partial pressure of helium? Okay, so our partial pressure of oxygen plus the pressure of helium is going to equal our total pressure. All right, if our total pressure is 7 and our pressure for oxygen is 1.5, we can subtract and get that the partial pressure of helium must be 5.5 atmospheres.